This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's question is to solve this quartic equation. It's a polynomial, its highest degree is 4, therefore it's called a quartic equation. It has integer coefficients, and if a human is asked to solve a polynomial equation, the assumption is that at least one of the solutions should be a rational number, a ratio of two integers. The rational root theorem tells us that if P on Q is a rational solution, where P on Q is in the lowest terms, so there is no common factor between P and Q, then we must have that the numerator P is a factor of the constant term of the polynomial. Now for this we ignore signs, so we can think of this as 256. And Q, the denominator of any solution to a polynomial equals to 0, also known as a root of the polynomial. The denominator Q, it must be a factor of the leading coefficient, the coefficient in front of the term containing the highest power. Again, we ignore sign and we see that the leading coefficient is a 1. Since the leading coefficient is 1, the only integer factor of 1 is 1, therefore the only rational solutions to this equation are actually integer solutions when Q equals to 1. Furthermore, any integer solution has to be an integer that divides 256. Now we can change signs here, so a factor could be 2 or -2 or 1 or -1 or 4 or -4 and so forth. Since 256 is 2 to the power of 8, its factors are simply the powers of 2, and so from the rational root theorem we conclude that the only possible rational solutions in x to this quartic equation are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32, plus or minus 64, plus or minus 128, and plus or minus 256. Now in general, there might not be any rational solutions, and at the other extreme, a degree 4 polynomial can have at most 4 solutions, and so we don't know if any of these are solutions. We know that not all of them are solutions. Between 0 to 4 of these are solutions, and the only thing left now is to substitute these into the equation in turn to see which ones solve it. For example, we can see if x is equal to 2 is a solution. So I substitute it in, negative 2 to the power of 4 plus 16 times 2 to the power of 3 minus 96 times 2 to the power of 2 plus 256 times 2 minus 256 is equal to, and if the answer is 0, then 2 is a root, but the answer is not 0, as you can check yourself by hand or with a calculator. Therefore, x equals 2 is not a solution to the original equation. You can nevertheless show that x equals to 4 is a solution to this equation. So we've found one solution, x equals to 4. Are there any other solutions though? The first method we will look at is the simplest method, although it's a bit tedious. We divide out the factor we found. Since 4 is a root, then x minus 4 must be a factor. Here's our original polynomial. I've multiplied it by -1 for convenience. I've just changed the sign of every single term, so its roots are the same. The solution to this equals to 0 is exactly the same as solving the original problem. And because 4 is a solution, you substitute x equals to 4 in here, you get 0 here. Then we know we have to be able to write it as x minus 4 times some other polynomial of a lower degree. We find this by performing long division, which I'll do on the next page now. We start by writing it just like a long division. We have it arranged in terms of largest coefficient to smallest coefficient. How many times does x go into x to the power of 4? Well, x to the power of cubed looks good. We then multiply this by this to get x to the 4 minus 4x cubed, and we now do the subtraction. We're subtracting the whole green expression from the red expression here. So x to the 4th minus x to the 4th is 0. Indeed, we chose this so that that would happen. We then end up with a lower degree polynomial. We'll have a degree 3 polynomial. Negative 16x cubed minus negative 4x to the cubed gives us negative 12x cubed. These other terms here just get brought down, plus 96x squared minus 256x plus 256. The process now repeats again. We have the leading term here is x, the leading term here is negative 12x cubed. How many times does x go into negative 12x cubed? The answer is negative 12x squared. We then multiply this by this to get negative 12x cubed plus 48x squared. Now we do the subtraction. We chose this coefficient here to make sure that the leading terms here cancel. They're equal to 0. 96x squared minus 48x squared gives us 48x squared, and all the other terms come down. Negative 256x plus 256. And we repeat again. How many times does x go into 48x squared? The answer is 48x. Do the multiplication. We get 48x squared minus 192x. Do the subtraction. The leading terms cancel because of the way we chose the term here. Negative 256x minus negative 192x gives us negative 64x, and the other term comes down. And finally, we have got over here, I'll do it in the same color, minus 64, which when we multiply it, we get negative 64x plus 256, and that of course leaves a remainder of 0. If it does not leave a remainder of 0, then either 4 is not a root of the original polynomial, or we made a mistake. Importantly, what we have shown is that our original polynomial is equal to x minus 4 multiplied by this polynomial that we found here. Indeed, division is the opposite of multiplication. By doing this division, we worked out what we had to multiply this guy by to get this one here, namely this polynomial here. From the previous page, we know that our original polynomial is equal to x minus 4 as one factor, and x cubed minus 12x squared plus 48x minus 64 is another factor. Now we repeat the process. We look for rational roots of this cubic equation here. By the rational root theorem, we know that the rational roots can only be plus or minus 1, 2, 4, 8, 16, 32 or 64, because these are the only factors of 64, and the leading coefficient is 1, meaning the only rational solutions are actually integers. By trial and error, by substituting x equals to 1, then negative 1, then 2, then negative 2, etc., by trial and error, we discover that x equals 4 is also a root of this cubic equation here. We can therefore divide x minus 4 from this cubic equation here to get this quadratic equation. And we then repeat the process, and we find that x equals to 4 is yet another solution to this, and we divide it out, we're left with x equals to 4, so eventually we find that our original polynomial is actually x minus 4 to the power of 4. This means that the only solution to the original polynomial equaling 0 is x equals to 4. There's one root with multiplicity 4. It's always good to check our calculations so we can go in the other direction. We can ask, what is x minus 4 all to the power of 4? Can we work this out and show that it equals our original polynomial? There's of course several ways of doing this. We could of course write this as x to the minus 4 squared times x to the minus 4 squared, work out x to the minus 4 squared and then square that one. Or we're going to use the binomial theorem, just because it gives us an opportunity to remind ourselves of what it is. The binomial theorem looks like this, but to apply it practically, it's easier to just remember the following basic rule, which of course follows by this, but when you do it practically, then this looks less scary. To compute x minus 4 to the power of 4, well, because there's a plus sign here, we write it as x plus negative 4 all to the power of 4. And then the summation here means we're going to add up a number of terms, and k goes from 0 to n. We see that our first term, it's going to be raised to the power of first 4, then 3, then 2, then 1, then 0. And our second term, negative 4, it's going to be raised to the power of firstly 0, then 1, then 2, then 3, then 4. So x minus 4 to the power of 4 is equal to some number, depending on this magical coefficient here, times x to the power of 4. That's the first one to the power of 4, the second one to the power of 0. In other words, we ignore it. Then the next term, we've got some magic coefficient here, times one power lower, x to the power of 3, and negative 4 to the power of 1. Then x squared, negative 4 to the power of 2. So x goes x to the 4, x to the 3, x to the 2, x constant, while negative 4 goes constant, negative 4 to the power of 1, negative 4 to the power of 2, negative 4 to the power of 3, negative 4 to the power of 4. The only thing remaining is to work out what these coefficients are. This means you have n things. How many ways can we choose k of them? There's a formula for this involving factorials, but we can also use Pascal's triangle to work out the values, which we're going to do now. Pascal's triangle starts with 1 and 1, 1. Then the rule is, for each subsequent row, we start with a 1, and then the next number we get is given by the sum of the two numbers above it. So we're going to get 1, 2, and then we end with a 1. Then 1 plus 2 is 3, 2 plus 1 is 3, end with a 1. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, end with a 1. And since we have got n here being the number 4, then it's this row that we want to have that tells us what the coefficients are. Precisely reading from left to right, 1, 4, 6, 4, 1. To finish our calculation, we just have to evaluate these powers and multiply them by the coefficients. So we get x to the power of 4, negative 4 to the power of 1 is negative 4, times 4 gives us negative 16 x cubed. Negative 4 squared is 16. 16 times 6 is 96 x squared. Negative 4 to the power of 3 is negative 64 times 4 gives us negative 256 x, and negative 4 to the power of 4 gives us 256. And this is indeed our original polynomial. For fun, we can apply Descartes' rule of signs. Given a polynomial, we just look at the sign of each of its coefficients. In this case here, we've got negative, positive, negative, positive, negative. This means that the sign changes 4 times. And Descartes' rule of signs says that the number of positive real roots is no more than the number of changes of signs, and moreover, the difference between the number of positive real roots and the number of changes of signs is even. So since there are 4 changes of signs, that means that we either have 0 positive real roots, or 2 positive real roots, or 4 positive real roots. Indeed, we now know that this factors as x minus 4, so it indeed has 4 positive real roots, each of them being equal to the number 4. When we were applying the rational root theorem, we had to test both positive and negative values of 1, 2, 4, 8, 16, 32, 64, 128 and 256. By using Descartes' rule of signs, we can actually show that we don't need to test for any negative roots as follows. If we replace x with negative x, then any negative real roots will become positive real roots, and vice versa. So take our original polynomial, replace x with negative x, and notice that it will not change the sign of the coefficient for even powers, and it will change the sign for odd powers. Therefore, in terms of this new polynomial, we find all its coefficients are negative, there are 0 changes of sign, and so therefore we know that there are no negative real roots to our original polynomial equation. This then means that in step 1 we don't have to check for negative 1, negative 2, negative 4, negative 8, negative 16, negative 32, negative 64, negative 128 and negative 256. They cannot be roots because there are no negative roots to this polynomial equation here equaling 0. Finally, perhaps the fastest way of factorising this polynomial is by seeing that these coefficients grow rapidly, and so perhaps there's, in a certain sense, a common factor that we can remove. But the way it works is as follows. First, each of the coefficients I write down in terms of its prime factorisation. So 1 here, 16 is 2 to the power of 4, 96 is 2 to the power of 5 times 3, 256 is 2 to the power of 8 for both these terms here. Now, this trick will work if I can find a number alpha such that alpha divides 16, alpha squared divides 96, alpha cubed divides 256, and alpha to the 4th divides 256. And we see here that if I want alpha squared to divide 96, then because the other terms here that also have to be divisible only have 2 in here, I'm only looking at 2 or 2 squared or 2 cubed, etc. Well, alpha squared 2 to the power of 5, the best I can do here is have 2 squared. If alpha is equal to 2 squared, in other words 4, then it will divide 16, it will divide 96, and it will also divide 256. So the largest alpha I can choose here, largest integer alpha such that alpha divides this, alpha squared divides that, alpha cubed divides that, alpha fourth divides that, is alpha equals to 4. In which case alpha squared 16, alpha cubed 64, and alpha to the power of 4 is 256. Then this polynomial here, by dividing its roots by 4, I get this polynomial here, obtained by simply taking my original coefficients and dividing each one by these numbers here. So x to the 4th divided by 1 gives me x to the 4th. Negative 16x cubed divided by 4 gives me negative 4x cubed. 96x squared divided by 16 gives me 6x squared. Negative 256x divided by 64 gives me negative 4x. And 256 divided by 256 gives me 1. So any roots of this polynomial will be 1/4 the roots of this polynomial here, because I've essentially divided every single root by 4 by doing this trick here. Technically, what we've really done is we've replaced the variable x here with the variable 4 times y. That means that all the roots will be divided by 4. When you do that, you're going to get some very large coefficients, and you divide all the coefficients by 4 to the power of 4, 4 being the largest coefficient here, to bring them back down, and you end up with this polynomial here. This polynomial here, we can now apply the tricks that we've learnt before. Either we apply the rational root test, and we see that the only possible solution here is 1 or negative 1, so that simplifies things. Or we know from Pascal's triangle that 1, 4, 6, 4, 1 corresponds to a row in Pascal's triangle, and that would immediately suggest we try x minus 1 to the power of 4. Once we know that x minus 1 to the power of 4 is equal to this polynomial here, then we know that to go back to the original one, we just have to multiply all roots by 4. So this would be x minus 4 to the power of 4.